Hey everyone, welcome back to The Explainer. So today we're unpacking a really fascinating 2026 paper by Suri, Khanna, and Sen, and it tackles a major, truly major, theoretical breakthrough in condensed matter physics: topological zero reflection points in multi-terminal quantum wire junctions. Okay, I know, that sounds incredibly intense, right? But stick with me here, because this research is fundamentally changing how we might design the macroscopic circuitry of the future. Basically, it's all about perfecting the flow of information at the quantum level.
Okay, let's dive right into this. Imagine you're driving, and you hit this massive intersection where a bunch of high-speed highways converge. In our everyday classical world, if you've got terrible traffic light management, well, you get an epic traffic jam. Cars slow down, they stop, maybe they even have to turn around. Now, in the quantum realm, when quantum particles like electrons hit a multi-wire crossroads, something remarkably similar happens. They don't just smoothly pick a lane and keep going. Actually, very often, they bounce right back. They reflect off the intersection, creating this massive quantum traffic jam that just completely destroys the efficiency and coherence we so desperately need in quantum circuits.
So, to really grasp how we actually solve this, let's look at the environment itself. A multi-terminal quantum wire junction is, quite simply, a microscopic intersection. It's the literal exact point where multiple, non-interacting quantum wires meet up. When an electron travels down one of these super tiny wires and hits the center, it faces a fundamental choice dictated by quantum mechanics. It can either scatter forward into one of the other available wires, or it can reflect right back down the wire it originally came from. And obviously, our goal here is to completely eliminate that reflection.
Here's our roadmap for today. We'll start with the quantum traffic problem, then look at perfect intersections, explore the topological shield, introduce magnetic flux, examine this really cool n=4 broadband phenomenon, and finally, look at spotting it in reality.
All right, part one, the quantum traffic problem, navigating the intersection.
So, when a particle approaches this microscopic junction, its fate is basically dictated by a specific set of parameters modeled by a scattering matrix. The authors highlight two absolutely critical competing variables here. On one side, you have E, the incident particle energy, so basically how much momentum our quantum car has as it rolls up to the intersection. And on the other side, there's T prime, the junction hopping amplitude. This represents how easily a particle can actually hop into the junction itself. Balancing these two exact things is the absolute key to clearing the intersection.
Moving on to part 2, perfect intersections, achieving zero reflection.
Now, what's really interesting about this slide is that the researchers discovered something genuinely remarkable. If you tune those specific parameters we just talked about, the energy E and the hopping amplitude T prime, just perfectly, the probability of the particle bouncing back drops to absolutely zero. Literally zero. The intersection just becomes completely transparent. But there's a catch. There are strict mathematical conditions. It requires junctions with a specific structural geometry, something called dihedral symmetry, and specifically where the number of terminal wires, n, is 4 or more. So if you have 4, 5, or 6 wires symmetrically arranged, the math guarantees these perfect, reflectionless points exist. There's also this neat even-odd dependence, but the big takeaway is that as you add more wires, converging to a large n limit, these optimal zero reflection points actually stabilize.
Which brings us to part 3. Topology, the protective shield.
Now you might be wondering, in physical reality, quantum circuits are deeply messy, right? They're full of defects and microscopic bumps. So how do these super delicate zero reflection points even survive? Well, the answer lies in topology, specifically an integer winding number associated with a phase of the reflection amplitude at the junction. I want you to think of this winding number as a deep mathematical cheat code that is embedded directly into the system's quantum geometry.
So the crucial point here is that this topological property provides this incredibly robust stability. Because the winding number has to be an integer, like a solid 1, 2, or 3, it can't just smoothly deform into some weird fraction. It essentially ties a mathematical knot that locks the zero reflection point securely in place. It acts as a literal protective shield against what the researchers call weak on-site disorder. Basically, this means that those tiny microscopic imperfections in the quantum wires, they won't destroy the perfect flow of our quantum traffic. It is topologically protected.
Okay, part 4, magnetic flux and broken symmetries.
Up to now, we've basically assumed the system respects time reversal symmetry. But what actually happens if we intentionally break that using an external magnetic force? We already know junctions with 4 or more wires achieve zero reflection naturally, but the researchers discovered that by threading a magnetic flux through a previously problematic 3-terminal junction, they could actually induce entirely new reflectionless points. No way, right? They literally used a magnetic trick to fix the quantum traffic jam.
Next up, Part 5, the n=4 broadband phenomenon. All right, prepare yourselves for this one because this is arguably the single most technologically relevant breakthrough in the whole paper. They looked really closely at a 4-terminal junction, so n=4, but this time threaded by a very specific quantum of magnetic force, a π-flux. This specific setup dramatically alters the quantum interference patterns within the junction.
And this brilliantly illustrates the ultimate prize of their research. Under these highly specific conditions, n=4 and a π-flux, as the authors write in the paper, the reflection amplitude vanishes over the entire energy band. I really cannot overstate how huge this is. Previously, zero reflection only happened at isolated, very specific points of energy. It's kind of like having to drive exactly 55.2 miles per hour just to catch a green light. But here, achieving broadband zero reflection across the entire energy band means the particle will not reflect back, virtually regardless of its incoming energy level. It is literally like turning a precarious tightrope into a massive, wide-open highway. For sure, this is an absolutely massive leap for designing robust, practical quantum networks.
Let's move to our final section, Part 6, Spotting It in Reality.
So how do we prove these points exist beyond just, chalkboard mathematics? Experimentalists look for specific real-world markers. First, they observe the behavior of Friedel oscillations. Think of these as measurable ripples in the electron density around the junction. The signature of true zero reflection is physically written into how these ripples behave. Second, they test the junction's stability against weak interactions. This basically confirms that our topological shield is actually holding that zero reflection point steady in a real, messy physical environment.
We've seen how balancing energy and hopping amplitudes, utilizing these awesome topological shields, and leveraging magnetic flux can create perfectly transparent intersections. Which leaves us with a really profound final thought. If we can successfully engineer physical networks where quantum particles never get stuck in traffic, always transmitting perfectly without reflection across a broad band of energies, how will perfect reflectionless quantum wires reshape the future of technology? From hyper-efficient quantum computers that don't lose data at their intersections, to flawlessly secure communication networks, mastering the quantum crossroads might just be the green light we need for the next great technological revolution. Thanks so much for joining me on this explainer, and keep questioning the science.